bad actually at all.
Yeah, that's the algorithm. Like a more general thing would be anything that doesn't behave similar to the rest of the data is outlier.
Yes, I would agree, but I think her point here was showing like what does feels like mean? Like how do we mathematically define? That's what she was big on
Yeah.
teaching is like how
Yeah.
do
So some kind of distance kind of thing. And if you take the distance as Euclidean distance, then you get the k nearest neighbor kind of thing.
exactly. Exactly.
Yeah. Data points that are unexpected and significantly different from typical examples. That is outlier.
Yeah. Yep. Yes. Okay, so objectives, learn what data are frequently considered outliers, learn algorithms for detecting outliers. So data points that are unexpected and significantly different from a typical example in the data set in some way. So weather data, if it's super high in Houston or super low in Houston, sorry, super high blood pressure, super high drug pricing. So that's pretty obvious. Outliers are not the same as unusual data. The low of 12 degrees in Houston is unusual, probably not an outlier. Low of 10 degrees in Chicago, a bit unusual, probably not an outlier. It's the combination of Houston, -12, that makes this difficult to believe. What?
So basically, 12 degrees centigrade is outlier for Houston. Doesn't mean it will be outlier for Chicago as well.
Oh, got it. Yes, 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 yes.
So that tip. So basically, like if you have X and one combined makes something an outlier, not the X and the Y values separately.
That makes sense. That makes sense.
So you have to look at the data point as a whole totally.
Got it. Yeah, like he or she was saying, like, is this an outlier?
Yes.
Is this an outlier? Is this an...
Yeah, probably not.
They can hurt. Why look for outliers? They can hurt the learning process, huge impact on least squares. Outliers have a
Yes. They have unusually large effect
because of the squared also too.
because like we're squaring. So anything that deviates a lot, it's too much weightage.
Nice. Okay, this can be dangerous. Change your model. Yeah, because it'll increase the error a lot, right? Are they really bad data? Values that defy natural laws. Negative blood pressure, that's not possible.
Yes.
Speed faster than light. Sometimes it's meaningful. Age 0 in an adult. ER. Value 99 to indicate unknown. It's a slippery slope. Okay. So that's just
So
saying like,
sometimes like the data is missing or something or unknown. So people put some really unusual values to indicate those.
yeah,
So like if the age is not available, they put it 0.
0,
So, but
90.
the 0 age can be a newborn also. So you have to be careful about those things.
Nice. Why look for outliers? Classically, two reasons. Classically, to remove them from the data because outliers can hurt the learning process. That makes sense. To find them for further examination because outliers might enhance understanding of data.
Yes.
Okay, that's cool.
Yeah. A third option would be to understand and decrease the influence of the outliers. So you can still do your analysis in the same manner, but don't use least squares. Use something slightly different from least squares, which will not put so much weightage to the outliers.
Got it.
So that's basically the idea of the robust regression.
Got it. Okay. Robust regression, that's what you called it.
Yes. Yes. Robust.
That helps identify outliers then as well in robust regression.
No, it doesn't actually identify outliers in true sense. It just basically changes the influence function in some way. So, for example, if you instead of doing let's say least squares, you do L1 kind of regression,
Mhm.
that is less prone to outliers. That
Got it.
would be one example of a robust regression. But even that is not robust enough for some people, so they want even more robust things, and there are a lot of choices there.
Got it. Okay. Okay. Find the outliers, computer security, fraud detection. Those are all good examples. Yes. Is it fraud? Outlier detection is an unsupervised task.
Yes,
Why?
because there's no way to really check if you correctly remove the outlier or not.
Yeah. We don't always know what the outliers look
Like
like.
there's no training data to learn which ones are outliers and which ones are not.
Got it. Okay. How to detect outliers. Two approaches. Distance-based. Outliers are very far from other points, most commonly used approach. Model-based. Outliers have very low probability of occurring. Flip a coin, observe nine heads. Okay, that makes sense. So distance-based and model-based.
Yes.
Coin flips. So if we're going through coin flips, we're saying if a data point has a very low probability, oh yeah, the nine heads is very low
Yes.
probability. So the
Yes.
coin is likely biased. So we would say that this is an outlier, nine heads is an outlier.
Yes.
Okay, yeah. Distance-based outliers. Okay, so this is where we're doing k nearest neighbors. A point is an outlier if it is far from all other points, defined in terms of k nearest neighbors. Given a data set X, D be the distance we want to compute. Yeah, so this one, it was like a iterative algorithm we did in class where she like started with a point, found like they
Yes. Find
defined
the nearest point, second nearest point, and so on.
exactly, find the nearest point. So we picked a point, find the distance to
Yes.
all of the points. Here we're doing two nearest neighbors, so I guess we're finding the
Yes.
top
Two
two
nearest points.
or top, sorry, smallest distances. Yeah, we want
Yes.
small
Smallest. Yes.
nearest neighbors, right? Yeah, okay. So we're doing those two are the nearest points.
Yes.
So then we just keep iteratively doing that. So now we pick
Yes.
this
For
one.
every point, we have to find the two nearest guys.
So then we found all of the two nearest.
Nearest number distance.
Wait, why does she not have 2 points? Oh, she just did the max,
I
whichever
think see
one.
that's the max. Yes, you have to somehow summarize them. You can do average or max. I think max is more meaningful.
So that's the next step is find the max distance point out of those two nearest neighbors.
Yes.
And then why did she highlight the things in red? What is m equals 3
Because
again?
those are very high compared to others.
Those are
For
very,
those 3 points, B, K, and I, the nearest neighbors are very far away.
oh
For
yeah,
all
yeah,
the other points, the second nearest neighbor is close enough.
yes, that makes sense. So these are yeah, these have the furthest nearest neighbors. Furthest nearest neighbors. Yeah. Okay.
Yes.
So that's
One
pretty
quick comment that if you are doing second nearest neighbor, it's better than one nearest neighbor because what if suppose there are two outlier points which are both far away from the whole data, but they are very close to each other. So they will be each
oh
other's nearest neighbor. But if you do second nearest neighbor, they will be getting caught.
yes.
So that's why we don't just do one nearest neighbor kind of thing. We do second or third or fourth, something like that. Like increase the number a little bit at least.
So that one will identify that close point, which will make sure, but that'll make it both
Yes.
outliers then as well too.
Yes.
That makes sense. That's a good call. So how do I define M here? M is my number of outliers.
I don't know what is M here. They have defined anymore.
M,
M is number of items, I think.
yeah, M is the number of outliers we are looking for. Yes.
Yes. Yes.
So X is the set of data points. O is a min priority queue. Yeah, this is
Yes.
exactly what we just did. Okay, K is okay. This is exactly what we just did. Are there any issues with the algorithm? M and
Yeah, you have to know M beforehand. That
yeah,
is a bad thing. And
hyper
K also. Yes. And then the computation time is very slow.
n squared there,
But
right?
there are better algorithms to do that.
Nested for loop, yes, n squared. Faster algorithm. If the Q is equal to, oh, this is the one we did in class. I'm okay on this, Ajay. We have a whole exercise on this in class. It's hard to show you.
Okay. Okay.
Yeah, we have like a data set, and then she made us do
Okay.
it by hand also. So then we have like the part, so we have to
Oh, okay, nice.
draw out the
Nice.
whole number.
Mm.
So I think this algorithm I'm okay with now. It once I did it in class, it made sense.
Okay.
We'll go over more of the theory though here. So why does this help?
Yes.
Max Q is an upper bound on distance to so distance to k near neighbor can be even greater if the new distance is not good enough
Yes.
to get.
So
Oh
you're basically doing some kind of pruning and trying to remove points which will never be outlier because their kth distance is already too small.
yeah.
So we are like making the algorithm a little bit more efficient and will run faster.
we can remove those points then, right? Yeah, we don't even have to evaluate. Store X in randomized order. That way you won't get unlucky and find all far points first. Yes, that makes sense.
Hmm.
So now our hyperparameters, which are K and M. So how to compute distance, classical method if X and Y. Yep.
Yeah, number of outliers. People like this is not really the optimal way to do this. What people usually do is once you have all those values, like the table that they created, right, of the second nearest neighbor chart, you will see that the most of the numbers will be small and then few numbers are really large. So do a cutoff between those two, and that will tell you how many outliers are there.
Got
So
it.
suppose most of the numbers are below two and there are 7, 8, and 9, then obviously 7, 8, and 9 are outliers.
Okay. Got it.
K usually is size of the data set dependent. You can do square root of n or something like that. Or maybe slightly smaller than that also is fine.
Yeah. N is the number of data points.
Yeah, n is the number of data points.
You can do square root of n then. Okay. She talked about this in class. Is this a Python? I forgot why this happens. Why does this happen in Python?
This is problem with floating point number. It's not Python specific. It's basically numbers which are not so like integers can be represented exactly. Floating point numbers which have denominator which is not a power of 2, like 3 by 10 or something. 3 by 10 is not a real floating point number, meaning
Oh,
there's no number which is exactly equal to 3 by 2 in the binary system, 3 by 10,
got it.
because all the binary numbers have denominator is 2 power n, right? So you
Uh,
cannot have a 10 in the denominator. So we can only represent it approximately.
yeah,
And that's why what you see as 0.3 is actually 0.30000 something.
got it.
So, and once you multiply and do some addition and all, this like error keeps creeping in and increasing, and eventually you will notice.
Got it. Interesting.
So that's why on floating points, you should not do equality check directly.
Yeah,
You should do something like distance is less than some small epsilon. So that's a better way to do things.
better than things. Okay, so model-based outliers. So this one was the second way. So this one was distance-based outliers. Now we're looking at model-based outliers.
Yes.
So basic idea, learn a model from what is typical.
Yes.
Might probabilistic might be least squares. An outlier is a
Yes.
data point with a low score according to the model. I didn't understand that, Sujay.
So we are trying to have a probabilistic model, let's say around our data or some kind of distance kind of model. These are equivalent things like least square is equivalent to normality assumption. So you can assume either the data is normal or you can do least squares kind of thing, which is same. And then based on that, we'll give some score to all the points. And then somehow the low squares will correspond to outliers.
Got it. Okay.
So one way would be like if you have a joint distribution, let's say normal, then you can estimate the mu and sigma square. And if you estimate the mu and sigma square, you can calculate the density at each of the points. And if the density is very low at one of the points, then it's probably an outlier.
Yeah. Yeah.
So
Yeah.
that's one way of thinking.
That,
Density very low, equivalently is x minus mu over sigma whole square is very large.
yeah, exactly. Yeah. Maybe
So
like
that means the z score is in absolute value is very large.
nice.
So that's like an alternate way of putting it.
Nice. Okay, buddy. I think we did a great job here. We covered two topics today. That's good. I think I'll be ready for those are the two big ones. Outlier. Let me see if there's something on this outliers handout real quick. Oh, this was the work. Oh, sorry. Yeah, this was the worksheet. So
Okay.
we went through this exercise and did it together.
Okay. Nice.
So we went through the algorithm there. That makes sense. So we did outliers handout, outliers. That's not necessary. We did generalized linear models. Regex. Ooh,
Oh, okay.
this is random. What was regex again? This one was like writing.
Regex is pattern matching on strings.
Can we do
And
find?
then different languages and pattern matching on strings.
Can we do 5 minutes of this today? Yeah, real
Yeah,
quick.
yeah, no worries.
Let me stop this recording
Yeah.
so
So this is a